An isosurface is a three-dimensional analog of an isoline. It is a surface that represents points of a constant value within a volume of space. In other words, it is a level set of a continuous function whose domain is 3D space. Applications. Isosurfaces are normally displayed using computer graphics, and are used as data visualization methods in computational fluid dynamics, allowing engineers to study features of a fluid flow around objects, such as aircraft wings. An isosurface may represent an individual shock wave in supersonic flight, or several isosurfaces may be generated showing a sequence of pressure values in the air flowing around a wing. Isosurfaces tend to be a popular form of visualization for volume datasets since they can be rendered by a simple polygonal model, which can be drawn on the screen very quickly. In medical imaging, isosurfaces may be used to represent regions of a particular density in a three-dimensional CT scan, allowing the visualization of internal organs, bones, or other structures. Numerous other disciplines that are interested in three-dimensional data often use isosurfaces to obtain information about pharmacology, chemistry, geophysics and meteorology. Implementation algorithms. Marching cubes. The marching cubes algorithm was first published in the 1987 SIGGRAPH proceedings by Lawrenson and Klein, and it creates a surface by intersecting the edges of a data volume grid with the volume contour. Where the surface intersects the edge, the algorithm creates a vertex. By using a table of different triangles depending on different patterns of edge intersections, the algorithm can create a surface. This algorithm has solutions for implementation both on the CPU and on the GPU. Asymptotic decider. The asymptotic decider algorithm was developed as an extension to marching cubes in order to resolve the possibility of ambiguity in it. Marching tetrahedrons. The marching tetrahedrons algorithm was developed as an extension to marching cubes in order to solve an ambiguity in that algorithm and to create higher quality output surface. Surface nets. The surface nets algorithm places an intersecting vertex in the middle of a volume voxel instead of at the edges, leading to a smoother output surface. Dual contouring. The dual contouring algorithm was first published in the 2002 SIGGRAPH proceedings by Tao and Frank, developed as an extension to both surface nets and marching cubes. It retains the vertex at the center of the voxel but adds a surface generation that leverages octrees to add support for geometry that adapts the number of outputted triangles to the complexity of the surface. Examples. Examples of isosurfaces are metaballs or blobby objects used in 3D visualization. A more general way to construct an isosurface is to use the function representation.